All right, so I'm Kundan Kadam from Konkley Observatory in Budapest, and today I'll be talking about planet formation via self-sustaining vortices. So this talk is a part of a conference which is called 5 Years After HL Tau. On the website, you can find more information about it. So here's the structure of the talk. I'll be talking about astrophysical context, some hydrodynamic modeling that we do, and some results. So the context in this case is planet formation. So you're very well aware of this fact that ALMA has revolutionized the field of planet formation and the observations of these young systems. So there's this iconic image of HL Tauri disk at the right-hand side where you have the grand design ring structure, rings and gaps. And since then, there are several systems discovered which show that the substructure is ubiquitous, not only in sub-millimeter wavelength, but in reflected light in infrared wavelength as well. But with sub-millimeter, like ALMA wavelengths, what you probe is the disk midplane. So that's the dust content of the disk. So that's the solid component. And that's very important for, crucial for probing planet formation. So the disk substructure and asymmetry such as gaps, rings, horseshoes, spiral lumps, inner holes, they seem to be a norm. So almost all disks have some kind of kinks in them. And that raises some fundamental questions. So is this an evidence of planet formation? Or these are the effects of planets which are already formed in the disk? And if it's the latter, how the planets can form so early in this disk? Because most of these disks are less than 1 million years old. So that puts severe constraints on the theories of planet formation. So in order to form planets in these disks, the dust from the interstellar medium, which is found via supernovae and so on, it has to grow about 13 orders of magnitude in size and 39 orders of magnitude in mass. So micrometer size dust grows to about meter size, and then to planetesimal, which are kilometer-sized bodies. So planetesimals are basically the building blocks of planets, and after that, the gravitational interactions can take over, and the interactions are dominated by n-body dynamics, which form planets. But getting from the meter size to these building blocks of planetesimals, there are some hurdles that stand in the way. So here I mentioned two of the barriers to the dust growth. So one is called meter size barrier, in which when the particle is of a certain size, it feels the maximum headwind in a gaseous disk. And what ends up happening is that the particle loses its angular momentum and just ends up accreting onto the star. And there's no more dust left in the disk. So that's a big problem of the models of planet formation. And another problem in terms of dust growth is called fragmentation barrier, in which you have a relative velocity of dust particles. If they approach each other at certain velocity, instead of sticking together, they disintegrate each other and limit their maximum size. So there are some theories, there's even one theory, it's called lucky few particles, in which the authors propose that some particles are lucky enough to survive up to planetesimals, and then on they can form planets. But these theories are not very satisfactory. And what we do is we try to probe these early phases of planet formation using hydrodynamic models. So we use a code called GFargo2. So this is based on the original Fargo code developed by Benitez Lambai and Frederic Massey. So it's so the latest version is Fargo 3D. You can look at their 2016 paper for the details, but Fargo stands for fast advection in rotating gaseous objects. So this is an algorithm in which the advection equation, they're solved in the local Keplerian frame of reference. So as a consequence, you have relaxed Courant condition, and the accuracy or the truncation error is also improved. So this particular version, GFargo2, is based on C++ and CUDA implementation, and is developed by my colleague Joel Rogali in Konkley Observatory as well. So this code conserves mass and angular momentum to machine precision, and it's solved on cylindrical coordinate system because of the symmetry of the problem. It also has n-body integrator for planetesimal interactions, but we don't use that in this particular case. So these are some of the equations that we saw for the gas dynamics. So you have the continuity equation, momentum conservation, you have energy equation, and all of these have to be have proper initial and boundary conditions as well, of course. So we also solve the dust components. So the dust is modeled as a pressurized fluid of constant Stokes number. So you have the continuity equation and momentum conservation for dust, and in the momentum you can see there's no pressure term on the right-hand side, but what you have is the back reaction term, or the F drag. So you can close these systems of equations by assuming some equational state like ideal gas. And then we also have gravitational potential. That's basically potential of the star plus the self-gravity of the disk, and something called indirect potential, which is the movement of star disk system about the center of mass. Now on to some results. Now, one crucial thing in this simulation is the prescription of viscosity. So canonically, it's assumed that the viscosity is caused by something called magnetorotational instability. So canonically, what we call it as Sekirashunyev viscosity prescription, in which the viscosity nu is proportional to some local properties of the disk, like sound speed and Keplerian velocity. And the constant of proportionality is just a constant. But in this particular case, we make a key assumption that the dust particles absorb the charged particles, so they reduce their concentration, and they thus reduce the MRI viscosity, because this magnetorotational instability depends on the concentration of the charged particles. Now at the bottom, you have the equation to specify how we calculate the alpha. And on the right-hand side, you have the exponents -1 and 1. So essentially, the alpha is proportional to the enhancement in the dust. So that is the dust to gas ratio at each grid location. And now when you have this alpha prescription, what happens is that if you try to solve these equations in 1D or do a linear perturbation analysis, what happens is that when you have a slight perturbation in the dust density, it reduces the local viscosity, and because of that, it accumulates the gas, basically due to the mismatch in mass transfer rate. So as a consequence, the dust accumulates towards the pressure maxima created by the gas, and that creates more dust concentration. So it creates a positive feedback loop. And what ends up happening is that you have these series of concentric rings that form in the disk. But we use this prescription with 2D evolution. So this is what happens in the G-Fargo code. So what you have is initially you had the viscous ring instability, but what we found is that those rings are not stable. They are Rossby unstable. So the ring breaks up into a multitude of small scale vortices. So here you can see the individual structure of the vortex, which is rotating in an anticyclonic direction. So these are initially formed at the location of the initial perturbation in the dust density. So this frame shows you the distribution of dust. So here we see evolution of mature vortices. So this is in a frame of reference rotating with respect to Keplerian velocity at this point. So that's 1 AU. And that's why some are rotating in one and some in the other direction. So what you might observe is that each vortex also creates these spiral waves in inward and outward direction, like a migrating planet. And the constructive interference in these waves creates a next generation of vortices. These vortices can propagate throughout the disk. Now here I show the dust of the gas and dust distribution in 1D and 2D. So you can see on the left-hand side, 1D, you just have these rings. And the 2D, these rings become Rossby unstable and create several vortices. On the right-hand side, you can see the flow pattern or the velocity structure of these things. So these are indeed anticyclonic vortices. Now, there's also possibility of the grand design ring structure that we see, for example, in HL tau. So at low densities, the recombination rate or the ionization degree is much less sensitive to the dust properties. It's dominated by the gas properties. So as a result, if you model this as a larger value of the minimum viscosity, the vortex formation is suppressed. So the only viscous ring instability is initialized, in which you have a series of concentric rings, but they don't break up into vortices. So there's a possibility that this theory would explain everything in one framework. And why are these results so important? So what we have is essentially a simple physically motivated model in which the local concentration of dust reduces the viscosity, which is very intuitive. So these vortices which are formed in the disk, they're secularly stable. So stable for over thousands of orbits. And that can help mitigate the drift barrier, because the dust, it stays in the disk. You can also overcome the fragmentation barrier because the local concentration of dust, or dust to gas ratio, exceeds unity at inside these vortices, which can trigger further instabilities like streaming instability, which can overcome the fragmentation barrier. So an individual vortex can collect a significant amount of dust of the order of 0.1 to 10 Earth masses. So they're ideal sites for forming planetesimals or even planetary cores, or cores of giant planets. So this is the first model to produce a large number of vortices in ordinary conditions of minimum mass solar nebula, so no special conditions required. So at the end, I'll leave you with this quote of Laplace, which was, he said that about 200 years ago. You can pause on this slide, and that's about it. Cheers.